registers that are used in digital system design. Normally registers are the knowledge which you need, which is very important because we also use registers in processors and all to store the information. Now what is registers? We all know about flip-flop, right? Flip-flop stores 1-bit information. Now this group of flip-flops or these flip-flops are grouped together to form a register which can store more than 1-bit information. Like it can store a data which is a word, which is word is always a 16-bit data, what we call. Okay, now if there are n flip-flops where each flip-flop can store 1-bit information, therefore if I say n flip-flop, it means it is an n-bit register. Okay, so if I say 16 flip-flops are there in a register, then we say it is a 16-bit register, and so on. So this is what a brief definition on registers. Now if you look into the registers, we normally use registers as a shift registers. Okay, so on the screen if you see, there are various types of shift registers. So normally we will work on these registers, which is CISO, CPO, PISO and PIPO. Now what does this mean here is, this is serial in, serial out. Okay, serial in, serial out. This is serial in, parallel out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. Okay, serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. These are the various types of registers that we normally look in the shift register. Okay, so now serial in, serial out can happen in two ways. Either it can work as a right shift register, or it can work as a left shift register. Now second thing what you need to know about the serial shift register is, or serial input that we give is, we give 1 bit each time as an input, we take output each time 1 bit. Okay, that is what serial in, serial out. So here you see data bit input, what we are giving 1 bit each time, whereas when you take out, you are taking 1 bit out at each time. So this is right side, it is moving, arrow shown in right side, so this is a right shift register. Similarly, you can also have a left shift register where the data bit moves or shifts towards left side. So when I say serial in, it means it is 1 bit input that we are going to give, 1 bit input each time, where serial out means 1 bit out each time, 1 bit out each time. Okay, that is what serial in, serial out. Now when I say serial in, parallel out means taking all bit together, taking all 4 bits as an output together. Okay, so that is what parallel means, considering all 4 outputs together, 4 bit output together is called parallel output. Here you see, when I say serial in, parallel out, I give input each time 1 bit, but when I take the output, I will take all 4 bit that is been given as an input each time, I will take all those 4 bit all together as an output, that becomes a parallel out. So that is what CISO and CPO is. When I work on PISO, parallel in, it means that I give all 4 bits at a time. So this is what parallel input, what you see, I will give all 4 bits all together at a time. But when I say parallel out, I will take all 4 bits at a time as an output. But when I say PISO, parallel in, serial out, I give all 4 bits all together as an input, but when I take output, I will take serial output. I will take 1 bit each time as an output. That is serial out, parallel in. Okay, so it means, see, serial in, serial out, parallel in, parallel out. So it is parallel in, parallel out. So I can work in this way: serial in, parallel out, serial in, serial out, parallel in, parallel out, parallel in, serial out. So that is the way I can work on shift registers. We also have rotate right and rotate left operation, which can also be used as a shift operation. Okay, you rotate right. Now what is the benefit of rotation is, when you rotate right, the LSB goes back to MSB. The same data keeps on rotating. That is what the benefit of rotation operation. If I say rotate left, the MSB comes back to LSB. So this is MSB and this is LSB, most significant bit and least significant bit. LSB becomes MSB in rotate left operation. Here LSB MSB becomes LSB here, sorry, MSB becomes LSB here, MSB becomes LSB here, LSB becomes MSB. After rotation, you see the least significant bit will be stored back to as a most significant bit. Here most significant bit is stored back as a least significant bit. This is the benefit of rotation. Okay, fine. So let us look into serial in, serial out shift register operation. Okay, let us look into serial in, serial out shift register operation. So what I'll do initially, okay, there are two modes of operation again in serial in, serial out. As we discussed earlier, we have two modes of operation. One is the left mode, the other one is the right mode. Now what we are seeing, the register diagram here is, it is a left mode shift register diagram, where data in is given at the right hand side and it is being shifted towards left. Okay, data in is given at the right hand side and then the data is being shifted towards left side and the output is taken at the left part of the flip-flop. Okay, so this is serial data in, whereas this is serial data out. Okay, initially all output will be 0. Initially all output will be 0. So let us assume initially the all output will be 0. Now what I will do, I will give data in 1 input. I will give 1 as an input to data in, and each flip-flop is connected to the clock pulse separately. Therefore every flip-flop is connected to a same clock pulse. Okay, so what is that? It is a synchronous type of operation what we have. Okay, therefore when I give input 1 to D in and when I press the clock pulse, this D in 1 is given to Q0. Now Q0 will become 1, where all others will be 0. So that is the first clock pulse output that you get, 1 0 0 0. Now again I will make D in 1, then therefore Q0 will be 1, means this D in what I gave, that comes to Q0, whereas Q0 was 1 in the initially, therefore that 1 will come here when you give the clock pulse. So therefore 1 here shifted towards left and then you see 0 0. Now again I will make D in 1, this Q0 1 comes to Q1, Q1 1 comes to Q2, where Q0 will store with the new value of D in that is being given. So again I will give D in 1 and press the clock pulse. This D in 1 comes to Q0 and that Q0 which was 1 earlier, that comes to Q1. Then Q1 which was 1 earlier, that gets shifted to Q2, whereas Q2 is 1 earlier, that gets shifted to Q3. So therefore this is how the serial input is been given, with all ones at the end. Now here, after giving all the data, I'll stop giving the data now. I'll just press the clock pulse. When you press the clock pulse, this D out 1 is first serial out. When you press the clock pulse, this will become 0, whereas this 1 gets shifted to Q1 and Q1 1 gets shifted to Q2, Q2 1 will get shifted to D out, and that would be the next bit 1. Next, again I will make 0, I will not give any input, so again this 0 comes here, this 1 comes here, and this 1 comes here, and that would be the third input, third output. Again give 0, this 0 comes here, this 0 comes here, and this 1 comes here, and that 1 will be taken as an output. Finally, when you press the clock pulse, all flip-flop output will be 0 again. All flip-flop output will be 0 again. Now this would be the serial data output that we took by pressing the clock pulse after giving 4 input of data. We don't give input after 4th input getting loaded to Q3, then we don't give any input, we try to give only the clock pulse. Therefore at Q3 whatever you take output is what the serial output that we get. So that is serial in serial out operation, and as we can see shifting is happening towards left side. This is a left mode serial in serial out shift register operation. Now here if you see, while shifting what we got, so D in was 0 initially, therefore Q0, Q1, Q2, Q3 initially it will all be 0. Whereas when D in is 1, so D in will become 1 for the next consecutive clock pulse. So D in is 1, where this will work because all these are negative triggered, edge triggered clock pulse what we are giving for each flip flop. Okay, so negative edge triggered clock pulse is what we are giving. Therefore the flip flop gets triggered only during the negative edge. Okay, so when negative edge is there, D in is 1, then only Q0 becomes 1. Q0 remains to be 1 until and unless the next clock pulse is arrived. So next negative trigger pulse will make Q0 1, and that Q0 1 will get shifted to Q1, therefore Q1 becomes 1 and remains to be in one state till the next clock pulse. Then when the next clock pulse is given, D in is again 1, therefore Q0 becomes 1, that Q0 goes to Q1 and that Q1 goes to Q2. Q2 is 1 now. Now in the next negative edge triggered clock pulse, D in again is 1, then that makes Q0 1, Q0 is shifted to Q1 which is 1, Q1 is shifted to Q2 which is 1, Q2 1 is shifted to Q3 now which is 1. So this is the clock diagram of the left mode serial in serial out shift register operation, where a negative edge triggered clock pulse is used here. That is the reason why the flip flop is getting triggered at the negative edge clock pulse whatever you see. When I go to the right mode, it is reverse, as exactly reverse operation of the previous left mode. What I do is I give input from this side, so I give input on the left hand side and I try to shift towards right and I take output at the right side. Okay, you used to give input from this side, now you give input from this side. So therefore D in is 1, when D in is 1 and press the clock pulse, initially all will be 0. Therefore when you give D in 1 and press the clock pulse, Q3 becomes 1, Q3 becomes 1, where that Q3 0 which was there, it goes to Q2 and so on. Now this becomes 1 in the next D in equals 1 clock pulse. Next this becomes 1 in the next clock pulse when D in is 1, and this becomes 1 when the next clock pulse when D in equals 1. Okay, so that is what you see here, 1 1 1 1. Now we are going from this side. Earlier we went this side, now we are trying to create from this side. So accordingly you can see the clock pulse now. Now the clock pulse works on the negative edge triggering only, as you see earlier. See here bubble, so it is again negative edge trigger only, but the only thing is right shifting is happening. Okay, so D in is 1 at this point as it is negative edge triggered, therefore Q3 becomes 1, Q2, Q1, Q0 will be 0. Now at this point D in is 1, so Q3 which was 1 gets shifted to Q2 and Q3 becomes 1 because of D in equals 1, and then other two will be 0. In this clock pulse, this one gets shifted to this one gets shifted to here, and this is 0. At the last fourth clock pulse, you see all will become 1 by shifting right side. This is the right mode serial in serial out operation. Now coming to serial in parallel out. Okay, as we do serial in, so serial in is D, Q3, Q2, Q1 and Q0. So you make D in equals 1, press the clock pulse. Initially all will be 0, right? Initially all will be 0. Therefore when you press the clock pulse, this becomes 1, whereas others will be 0, right? 1, 0, 0, 0. Now in the next clock pulse, again when D in is 1, Q3 will be 1. That 1 of Q3 will be shifted to Q2, where this 0 will come in. Therefore this becomes 1 now. In the next clock pulse, when D in is 1, Q3 becomes 1, but Q3 whatever it is there, it comes to Q2, this comes to Q1 and Q1 comes to Q. Therefore this becomes 1 now. Again give the fourth bit as an input, that gets loaded to Q3. When you press the clock pulse, content of Q3 comes to Q2, Q2 comes to Q1, whereas this Q1 comes to this. Now all are 1. All inputs are 1. Now when you take all these 4 outputs all together, like how I have written here, then this becomes the parallel out. This becomes the parallel output. So while giving input, so I'll take all these 4 bits all together, that becomes the parallel out. While giving input, we gave serial input here. Each time only 1 bit input was given, but while taking the output, we take all these 4 bits, that becomes parallel out. Now coming to parallel in serial out. Okay, coming to parallel in serial out. So here the first thing is we need to load the output with we need to load the input with parallel data. Okay, we need to load the input with parallel data. So if I say input is 1 1 1 1, I should see through that this A3, A2, A1, A0 will be 1, and all 4 bit parallel input should be given. So for that we need to have load operation. Okay, so loading operation will work when G1, G2, G3 is G1, G2, G3 AND gates are activated. AND gates are activated. Okay. Now when I give input 0, for the shift load bar, shift will be 0. It means that shifting operation should not happen while loading the data. That is what it means. Okay, when I give input 0 for this particular point, then shift will be 0. So shifting operation should not happen. So therefore 0 means load operation, 1 means shifting operation for this particular input. For this particular input, this is the condition. 0 means load, 1 means shift. Because when 0 is there, this NOT gate output will be 1, and that 1 will be given to this AND gates. Whereas 0 direct is given to this G4, G5, G6. So therefore when input is 0, then G1, G2, G3 is activated, whereas G4, G5, G6 are deactivated. So therefore the output of G4, G5, G6 will always remain 0. The output of the AND gate G4, G5, G6 will always remain 0 when the input is 0 for this, because it is directly connected to this particular point. Whereas when input is 0, then the NOT gate output will be 1, and that 1 will be given to this input of G4, G1, G2, G3. Now whatever the data that you give for A3, A2, A1, A0, whatever the data that you give for A3, A2, A1, A0, for example, I'll give 1, then those inputs are given through this AND gates. Anyway, A3 is given directly to D3, but A2, A1, A0 is given through AND gates. Now as it is activated, G1, G2, G3 are activated, one of the input is 1, where the other input is what you give for A0, A1, A2, that gets ANDed with 1, and you get the same data output with G1, G2. Now you give 1, 0, 1 for example. My input is 1, 1, 0, 1. Now 1 ANDed with 1 gives you 1. 1 ANDed with 0 gives you 0. 1 ANDed with 1 you give 1. Now you got 0 OR with 1 is 1, 0 OR with 0 is 0, 0 OR with 1 is 1, and this is 1. Therefore, see the input what it got loaded is 1, 1, 0, 1. 1, 1, 0, 1. This is the loading operation that we normally see. Now when input equals 1, now when the input equals 1, input for this I am saying, if the input for shift bar load bar is 1, then you see as this is 1 now, I'll just erase this. I've loaded already the input now. As this is 1 now, this NOT gate output becomes 0. NOT gate output becomes 0. Therefore, this G1, G2, G3 is now deactivated. Where G4, G5, G6 is activated. So once they G1, G2, G3 are deactivated, then that becomes 0, 0, 0. Whereas G4, G5, G6 is now activated. Therefore, this 1 whatever we had will be as an input for the second input of each gate. Now what would be the input, second input of this G4, G5, G6? That is the output that we are giving. Now you see the output is given here. Now for example, if the output is 1, 1 is given to G4, and 1 OR ANDed with 1 will give you 1, 1 OR with 1, 1. So it means that this AND gate G4, G5, G6 will allow you to connect with Q3 to D2. Similarly Q2 to D1, similarly Q1 to D0. So when they both are connected, and if you keep on pressing the clock pulse, then they work as a shift register, like how I have explained in the previous part, serial in, serial out, or serial in parallel out, whatever I have explained. When Q3 is directly connected to D2, okay, this AND gate allows you to connect Q3 to D2. Whatever the data given to Q3, that data is given to D2 now. Whatever the data that Q2 had, that will be given to D1 through gate G5 because they are activated. Now whatever the data given for Q1 through G6, it is being given to D0 now. Okay, so therefore when I give direct output to inputs here, when I keep on pressing the clock pulse, then that behaves as a shift register. Okay, so therefore initially by keeping this shift bar load bar, shift slash load bar 0, we have loaded the inputs parallelly, and this shift slash load bar, by making it to 1, we are now shifting the data shifting the data 1 bit each time, which is serial shifting, which we are doing here. So this is the diagram of parallel in, serial out, and whatever I have explained till you now, that is how the particular gate works. So my suggestion, if you couldn't understand the explanation with one listen, you please rewind the video and listen it again. I hope listen it slowly so that you will be able to understand the explanation what I have done. Coming to parallel in, parallel out. So it's quite simple. So parallel in, I'll directly give as an input to each flip-flops, and I'll take, when I press the clock pulse, what happens? Inputs are been loaded, and again if I press the clock pulse, that input comes out to the output. So parallel in, so I give 1, 0, 1, 1 for example, and press the clock pulse. This inputs whatever is given comes out to the output 1, 0, 1, 1. I'll directly take that as an output. I don't need any shifting operation here. I give parallel input, I take parallel output by just pressing one clock pulse. By giving only one clock pulse, I got the parallel out. No shifting is required in parallel out. Only in serial operations we see shifting, but not in parallel out operations. Okay, coming to bidirectional shift register. Bidirectional means it can either work as left mode or it can work as right. So when I have one single flip-flop register diagram to work as both left mode and right mode, then I should give a choice for this. Choice means, for example, if choice equals 1, it should work as a left mode. If choice is equal to 0, it should work as a right mode. So in that way, we need to create a design so that a choice is given in the circuit where with that choice it can either work as a left mode or it can work as a right mode. So that choice, whatever we are giving, is this NOT gate, whatever it is connected to this particular right/left bar. Now if the input for this particular right/left bar is 0, then for 0 it works as a left operation, left shift or left mode. If this input is 1, then this works as a right mode. Okay, now you see how it works. This line what you see here, this line what you see here, this line is connected to G1, G2, G3, G4. G1, G3, G4, right? So therefore, when I give 1 as an input to this, if I give 1 as an input to this, then 1 makes G1, G2, G3, G4 and gets to get activated. Whereas G5, G6, G7 and G8 deactivated. So therefore, when G1, G2, G3, G4 is activated, you see serial data is from right side is given to G1 and you are shifting it towards right side. Okay, so therefore when G1 is activated, G5, G6, G7, G8 is deactivated, then this output will be 0 for these gates. Whereas one of the input of this G1, G2, G3, G4 will be 1 because 1 is connected directly to these gates. Now whatever the input I give here, for example, if I give 1 as an input, that 1 ANDed with 1 will give you 1, then 1 OR with 0 will give you 1. So the first serial input came into DA from left mode. Now you press the clock pulse, that DA1 gets stored with QA, that comes to QA. Now this QA1 and 1 is odd with 1. That 1 is odd with, means 1 and 1 is ANDed, so you get 1. 1 is odd with 0, you get 1. So therefore, see the shifting operation is happening now. Now DB is 1, press the clock pulse, DB comes to QB, where QB comes to G3 and that becomes 1, 1 OR with 0 will 1 and DC becomes 1. See, DA was 1, get shifted to DB and that DB got shifted to DC and that DC will now get shifted to DD. Initially, when this one is shifting, meanwhile you also give other inputs here. That input keeps on shifting when this one is shifting. Okay, now if you give 0 here, this becomes 0 and that 0 will come here and the next data of DB will be 0. This 0 comes here. So this is how the shifting operation will happen. Okay, so each time when you give the inputs, when you keep on pressing the clock pulse, that input will be shifted each time. So you are doing right shifting here, right? We are doing right shifting. Therefore, when this is 1, right shifting will happen. Now when this is 0, this G1, G2, G3, G4 will get deactivated. G1, G2, G3, G4 gets deactivated because 0 is directly connected to G1, G2, G3, G4 now. Whereas that 0 is given to NOT gate and NOT gate gives 1. Therefore, that 1 will now be given to G5, G6, G7, G8. Okay, therefore, because of 0, G5, G6, G7, G8 is activated. Okay, therefore, this output of G1 is 0, G2 output is 0, G3 AND gate output is 0, G4 AND gate output is 0. Now, where is the data coming to G5? So, see here, now we will start from G8 because the serial data is given here now. So, G8 will be 1 in the beginning, that 1 is ANDed with 1 will give you 1 and that 1 ORed with 0 will give you 1. Press the clock pulse, QD will be 1. Now, see, QD is given back to G7. So, therefore, this 1 is given back to G7, 1 ANDed with 1 will give you 1, 1 OR with 0 is 1. Now, that is DC. Press the clock pulse, QC becomes 1. Now, that QC is given back to G6. Therefore, 1. 1 ANDed with 1 is 1, OR with 0 is 1, and press the clock pulse QB. See, QD got loaded to DC and QC. QC got loaded to DB and DB pressing clock pulse QB became 1. Now, you see what process is happening. We are shifting towards left side. We are shifting towards left side. So, therefore, I hope now you people understood what is bidirectional shift register and how it can be designed by using an extended gates AND gate and OR gate connected to each inputs of the flip-flop. Okay, and this is the main choice that we give here, where a NOT gate is also connected, and that makes right/left bar, where one input to this will make the flip-flop or the register to work as a right shifting, whereas 0 input to this will make the flip-flop to work as a left shifting. Okay, this is bidirectional shift registers. The next one is the bidirectional shift register with parallel load. Okay, so here in this particular diagram, we have added one more AND gate. Okay, one more AND gate. Therefore, we are giving 3 choices here. 3 choices are given. Okay, so 2 choices it is easy to define where a NOT gate is used. Okay, 0 is one choice, output of the NOT gate is 1. So, 2 choices can be given through a NOT gate. But we are giving a 3 choice now. What is that? We are also giving a parallel input now. Parallel input, serial in, where left shift also happening and right shift also happening. And we also taking parallel out. What are the process we are doing? We are giving parallel in and we also taking parallel out in this particular diagram. We are giving serial in, serial out. We are also doing this. But here in serial out, we are also working on left mode and right mode. All these are given. All these operations should be done in a single diagram. That is what we are doing. Parallel in, parallel out, serial in, serial out, where in that again left mode and right mode operation which we are working on. So, how to do this? How to work on this particular choices that should be given. So, if I give first choice, it should work as parallel in, parallel out. If I give second choice, it should work as serial in, serial out in left mode. If I give third choice, it should work on serial in, serial out mode as right shifting. So, 3 choices should be given. So, for that we use 2:4 decoder. This decoder is what which is used here. Now, I hope you all know that decoder is like a demultiplexer which basically works on the selection inputs. Okay. Now, these selection inputs are SL1 and SL0. These selection inputs are SL1 and SL0. Now, if SL1 and SL0 are 0, 0, then the process what we are working is parallel in, parallel in. Now if SL1 and SL0 is 0 1 0 1, then it works on serial left mode input, okay, left shifting, so you give input from here. So 1 0 serial right mode in, whereas for 1 1 it doesn't work. For 1 1 it doesn't work, means for 1 1 we don't give anything. That is what this 3, if you see, it is left blank. Okay, so 0 0 this will be selected, 0 1 1 will be selected, 0 1 0 2 will be selected. Okay, so now let us look into that, how it works. Okay, as we see 0 0, this will be selected, this is for 0 0, this will be selected, and that is given to this AND gates. Okay, so this is the 0 input of the decoder, this 4 AND gates are connected, and if you properly see, one of the input of that is connected to parallel input lines, this one. Therefore, if this AND gate, these 2 AND gates are deactivated, therefore these 2 AND gates will be 0 0 0 0. Now you give parallel inputs as 1 1 0 0, for example. That 1 will come here, get ANDed with 1 which is given through the decoder. Therefore, this 1 ANDed with 1 will give you 1, this 1 ANDed with 1 will give you 1, 0 ANDed with 1 will give you 0, 0 ANDed with 1 will give you 0. Now see, these 3 are given to OR gate. Therefore, when I OR this 0 1 0, I will get 1. So I will get 1, and this 0 1 0 will give me 1, this 0 0 0 will give me 0, this 0 0 0 will give me. This is how the middle AND gate, when it is activated, it is giving this parallel input to the flip-flops. Parallel input to the flip-flops. When I make 0 1, see 0 1 will select this line 0 1. This line is given to the third one. Now this is activated. Now what you can see is this gets activated, third one. Okay, so therefore the other AND gates are deactivated. The other AND gates are deactivated. So this both will be 0. Now this third gate is connected to this, so this will be 1 1, this will be 1, second input of each gate will be 1. Now if you see, serial data is given in the left side, and now that is get loaded to the input of D flip flop. Press the clock pulse, it comes to QD, and that is given back to this AND gate. DC, then QC. QC is given to DB. DB, press the clock pulse, QB. So this is doing what? Left shift. Okay. So when 0 1 is there, you can say this is left shift is happening. Serial in left shift mode. Now coming to next second flip input 2 of the decoder. When it is 1 0, you see it is connected to this AND gates. Therefore now what happens? Now what happens? This is activated and this both are deactivated. This is activated, this is activated, this is activated. Therefore the output of these 2 AND gates will be 0 now. Now as this is activated, you see serial is data given from the right shift. Therefore once this data is given, that gets ANDed with this 0 0. Therefore the same data what you give to this AND gate will come here. and then when you press the clock pulse, DA becomes QA. Now QA is given to this AND gate as a second input now. Again this output will be selected now when you press the clock pulse, that is given to DB. So QA was given through this AND gate and that is given to DB, and when you press the clock pulse, that is given to QB. Now see, if you properly see, it is doing right shift operation. Therefore, activating this gate will do right shift operation. So therefore, if you see that these 3 AND gates, whatever I have written here for each flip-flop, the first AND gate does right mode, middle one is for parallel in, whereas the third one is for left mode. Now to take the parallel out, connect just direct QA, QB, QC, QD to the output ports, that gives you parallel out. Okay, so this is how the bidirectional shift register along with the parallel loading option is given, and decoder is the main component here which allows you to work on 3 choices. Okay, so you can rewind the video again if you want to listen it and understand it in a much better. Now coming to universal shift register. Universal shift register in the sense, it can work as serial input, it can work as parallel input, serial out. So all CISO, CIPO, CISO, CIPO, PISO, PIPO, all 4 operations should be done in one single registers. So see here, so for that particular purpose, multiplexers are used. For each flip-flop, input is connected through the multiplexer. Now multiplexer is what? 4:1 multiplexer. Okay. Now S1 and S0 is there. If S1 and S0 is 0, 0, I0 will be selected in each flip-flop. S1 is 0, 1, I1 will be selected in each flip-flop. Then 1, 0, I2 will be selected in each flip-flop. 1, 1, I3 will be selected in each flip-flop. This is I0, I1, I2, I3, I0, I1, I2, I3, I0, I1, I2, I3, I0, I1, I2, I3. Each flip-flop, if you see, 1 is given to 0, 1 is given to 0, 1 is given to 0. Okay. So when I say I3, I2, I1, I0, then that option will be parallel input, and that input is taken from the fourth input bit of multiplexer, which is nothing but I3. That happens only when S1 and S0 is 1, 1. So when S1 and S0 is 1, 1, this is parallel input which we are giving. Okay. Now here we are giving serial input for shift left is 2. Okay. So therefore that is I2 is shift left operation. I2 is shift left. Similarly, I am giving serial input for shift right at I1. Therefore, when I say I1, it is shift right. Whereas I0 is what we are giving here. So I0 would be the what do you say? It has been short to give you a serial output operation. So I0 would be serial out we can take, or we can also say it is a no change condition. For 0, it remains to be no change, it remains to be unchanged condition. Okay, when I take an output from each flip-flop output, that becomes the parallel out. So this table, whatever I have written, is very, very important. 1, 1 parallel in, 1, 0 I2 shift left, 0, 1 I1 shift right, 0, 0 no change. So this is the universal shift register that you can look into, and based on this selection inputs S1 and S2, the input of the multiplexer will be selected. Based on that input selected, it tries to work on in this way. So when I0 is selected, the flip-flop remains as it is, no changes will happen in any of the flip-flops. Whereas when I1 is selected in the multiplexer, this particular flip-flops will work on shift right operation. When I2 is selected in each multiplexer, then this flip-flops will work as a shift left operation. When I3 is selected in each multiplexer, then this flip-flop will work as a parallel in and parallel out operation. Okay, so with this, the type of registers are covered, and from next video we will see how counters are designed. First we see the basic introduction on counters, and then we see how to design synchronous and asynchronous counters, okay, with different mod values. Okay, thank you.